Previously, we have been discussing about the impulse response of an LTI system, and using the impulse response of the LTI system, we saw how we could compute the response of the system to any arbitrary input x of n or x of t, depending on whether the system is a discrete time system or a continuous time system. So if we know the impulse response of the system, whether it is discrete or continuous time, then we can compute the output of the system for any arbitrary input by performing the convolution between the input signal and the impulse response. And we have seen in the previous two lectures how to perform this convolution operation itself for the discrete case as well as the continuous time case. And we illustrated that with examples in the last two lectures. Now, in today's lecture, we will see some properties of the LTI systems, and in the process also understand some of the features of the convolution operation itself. The first feature of the LTI system is that if the system is LTI, that is linear time invariant system, then the system is completely defined or characterized by its impulse response. Or in other words, if we know the impulse response of an LTI system, then we know everything about that system. That means it is completely defined by its impulse response. And that applies only if the system is a linear time invariant system. So for an LTI system, if we know its impulse response, h of n or h of t, depending on whether it's a discrete time or a continuous time system, then that system is completely described by its impulse response. Okay, and that applies only if the system is a linear time invariant system. So that's the first observation that we see. And consequently, what this also means is that if the system is a linear time invariant system, then the impulse response that we have for a particular system will be applicable only for that particular system. There will be no other system which has the same impulse response. Okay, so we have it's h of n is the discrete impulse response for the discrete system, and h of t is the impulse response of the continuous time case. So depending on whether the system is a discrete or continuous time case system, we can completely describe the system based on its impulse response. Okay, and that also implies that there will be no other system which has the same impulse response. However, that does not apply to a nonlinear system. If the system is a nonlinear system, then it is not completely described by its impulse response. We need further information to characterize that system. So that's the implication of this convolution operation. So if the system is nonlinear, so let's mention that. Then it is not completely described by its impulse response. Okay, so this feature that the system is completely described by its impulse response applies only if the system is a linear time invariant system. If there is non-linearity, then that statement is invalid. That means the impulse response is not enough to completely describe the non-linear system. So we'll take an example here, and we will see a simple case of an impulse response h of n in the discrete case, where h of n is given to be equal to 1 only for two specific values of n, when n is 0 and n is 1, and for all other values of n it is equal to 0. So that's 0 otherwise. Okay, now if we had to find the response of the system to any arbitrary input x of n, then the output y of n is going to be the convolution between the input x of n and the impulse response h of n. Now that's basically the convolution sum x of k times h of n minus k for k equals minus infinity to infinity. But now since the h of n term is defined only for n equal to 0 and 1, and it is non-zero only for these values of the argument of h, right? So h of n minus k here is non-zero only when this n minus k is either 0 or 1. For all other values it is 0. So what are the two possible values of k for which n minus k is non-zero in this case? So that will give us the value of y of n. So now basically we want to find what is the value of k at which n minus k equals 0 or 1. So n minus k is going to be equal to 0 when n equal to k. So when n is equal to k, n minus k equals 0, and let me write that in a different way. Rather than saying when n equal to k, I'll say when k equal to n, right? So when k equals n, n minus k equal to 0, and when k equals n minus 1, then we have n minus k equals n minus 1, which is equal to 1. Okay, so these are the two values of h of n minus k when this argument is either 0 or 1. That is when we have h of n equal to 1. For all other values of the argument, this term is going to be 0. This h of n minus k will be 0, and 0 into anything will be 0. So we are interested in the summation only for k equal to n and for k equal to n minus 1. So when k is equal to n, this summation term here will be x of n into h of 0. And when k is n minus 1, it will be x of n minus 1 into h of 1. So we'll have for h of 0 and h of 1, which is equal to 1, right? So now the expression y of n will become equal to x of n times h of 0, which is equal to 1. So x of n into 1 plus x of n minus 1 times h of 1, which is also 1, so into 1. So the input-output relationship for the system is x of n plus x of n minus 1. And if this system is a linear system, okay, if this is describing a linear system, then there will be no other system which has this input-output relationship. So if we know this h of n, then there will be no other LTI system, linear time invariant system, which has the same impulse response. So that means this impulse response completely characterizes or describes this LTI system. And based on that information, we can compute the output of the system for any input signal x of n. And what we see basically is that given this scenario, the output of the system for any input signal x of n is going to be the sum of the current value of n and the previous value of the input x of n, right? So that is basically the response of this particular system. Now, if the system is nonlinear, right, then in that case we will see that there can be multiple systems which have the same impulse response. So suppose we have an input-output relationship of a system which is given as suppose the output y of n of a system is x of n plus x of n minus 1 the whole square. So okay, suppose the output of a system is the square of the sum of the current input and the previous input, okay, Now that's a non-linear system because it is having a square term here, so that represents a non-linear system. And again, the impulse response of the system is the same as this previous impulse response. That means this h of n is defined only for n equal to 0 and 1. That's why we have this term only for n equal to x of n and x of n minus 1, because this h of n minus k is non-zero only when k is equal to n or k equal to n minus 1. So in place of k we put n, and in place of k we put n minus 1. So that's basically saying that this system is also having an impulse response which is given as h of n equal to 1 for n equal to 0, 1 and 0 otherwise. Okay, so that's the impulse response of this particular non-linear system. Now we can give an example of another non-linear system. For example, we can just make it as power 3, for example. Even then the impulse response is the same. So that means the same impulse response is applicable to multiple non-linear systems. So the impulse response is not unique to a specific system. So therefore the impulse response does not completely describe this system. Okay, so we can give another example, say y of n equals x of n plus x of n minus 1 the whole cube, for example. That's also a nonlinear system which has this same impulse response. So this system is also described by the same impulse response h of n. And similarly we can use another example where we can have y of n equals the maximum value of x of n and x of n minus 1. So that's the maximum of x of n comma x of n minus 1. That means the system gives an output which is the highest of the current input and the previous input. Okay, again, why it is comparing only the current and the previous? Because the impulse response is non-zero only when n equal to 0 and 1. So it is choosing between the current and the highest value between the current and the previous. So that means this same impulse response is applicable for this system as well. So there are multiple non-linear systems which have the same impulse response. So therefore we say that for a non-linear system, the impulse response does not completely describe the system, as we have stated here. Okay, so if the system is nonlinear, then it is not completely described by its impulse response. So let me underline that statement here, and that's very important. So the impulse response completely describes or characterizes the system only if the system is a linear time invariant system. Okay, now we see that there are three different systems here. The first equation here, the second equation over here, and the third one here. All of these three systems have the same impulse response. So there are multiple nonlinear systems having the same impulse response. So we'll write the same statement here. Multiple nonlinear systems having the same impulse response. Okay, and in a similar way we can talk about it even in the continuous time case, where instead of x of n and h of n, we will write it in terms of x of t and h of t. Okay, so the feature or the statement that the impulse response completely describes a system is valid only if that system is a linear time invariant system. If the system is non-linear, then that statement is not applicable, because there can be multiple systems which have the same impulse response. The next property of LTI systems and the property of the convolution operation that we're going to see is called as the commutator property. Okay, and as you know from the name, commutative property basically means changing the order of the convolution does not change the output. So that means x of t convolved with h of t is the same as h of t convolved with x of t. That's called the commutative property. So it's basically like an addition. Addition is commutative. 2 plus 3 is the same as 3 plus 2. Multiplication is also commutative. 2 into 3 is the same as 3 into 2. Similarly, convolution is also commutative. That means x of t convolved with h of t is the same as h of t convolved with x of t. And this equation is for the continuous time case. Similarly, for the discrete time case, we can write it as x of n convolved with h of n is equal to h of n convolved with x of n. So changing the order of the functions in the convolution operation does not affect the result. So that's called as the commutative property of convolution, and hence the commutative property of the LTI system itself, because x of t convolved with h of t is nothing but the output of the LTI system. So the output of the LTI system is not affected if we replace the input with the impulse response and the impulse response with the input. So when the input is x of t and the impulse response is h of t, we get an output y of t. And if the input is h of t and the impulse response is x of t, then we get the same output as well. That's what it means. Okay, so that's the first property of LTI system, and that is applicable to both the continuous time case as well as the discrete time case. Again, for those who are interested, if you're interested, you can read from the text and check the proof. In fact, you can do some basic algebra when expanding the convolution integral or convolution sum, and play around with interchanging these these functions and see that it will result in the same answer. Okay, I'll leave it leave the proof as an exercise for those who are interested to do it, but it is a fairly straightforward proof. So we are not going to look at any of the proofs of these properties, but you should be familiar with these properties and you should know how to use these properties to perform certain calculations and to analyze and solve the input-output relationship of systems. Okay, so that's the first property, which is called as the commutative property. The next property is called as the distributive property. And the distributive property gives us an ability to look at parallel systems. Okay, when you have two systems in parallel, we talked about system architectures a few lectures back, and the distributive property allows us to have a better understanding of what the how a parallel system can be replaced by a single system. So let's look at that. So the distributive property is basically saying, I'll write it in the continuous time case first. Suppose we have an input signal x of t convolved with h1 of t plus h2 of t. Okay, so it is convolution with the sum of h1 of t and h2 of t. So that is basically equal to x1 of t convolved with, so not x1, that's x of t. Okay, that's x of t convolved with h1 of t plus x of t convolved with h2 of t. So that's the distributive property. So it's like 2 into 3 plus 5. That's 2 into 3 plus 2 into 5. Similarly, the distributive property of convolution operation says that x of t convolved with h1 of t plus h2 of t is the same as x of t convolved with h1 of t plus x of t convolved with h2 of t. Similarly, we can write it for the discrete case as well, as x of n convolved with h1 of n plus h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. Okay, to understand this distributive property and how it is useful in analyzing systems, let's look at the example of parallel systems and try to understand how this distributive property can be useful in interpreting and understanding parallel systems. So we have this example of a parallel system. Okay, the system on top, let's say it has an impulse response h1 of t, and the system at the bottom has an impulse response h2 of t, and for some input signal x of t, the system on the top, it produces an output. Let's call it as y1 of t, which is equal to x of t convolved with h1 of t. Similarly, the system at the bottom, let's say it produces an output y2 of t, which is the convolution of its input x of t with its impulse response h2 of t, and both these get added to produce the overall output y of t, which is the sum of these two, right? It's just x of t convolved with h1 of t plus x of t convolved with h2 of t. Now this summation, so the y of t that we have in this equation here, in this system here, y of t is x of t convolved with h1 of t plus let me write that more specifically. It is equal to y1 of t plus y2 of t, because this y of t is the sum of y1 and y2. So that is basically equal to x of t convolved with h1 of t plus x of t convolved with h2 of t. And because we can write that as x of t convolved with h1 of t plus h2 of t by using our distributive property, right? So now we can write this separate convolutions as x of t convolved with h1 plus h2 of t, right? So that's exactly what we have done here. Or basically what that means is we can replace this system, this combination of these two parallel systems with a single system whose impulse response is the sum of these two impulse responses. That is what it means. So basically what we're saying is that if we have a system whose impulse response is h1 of t plus h2 of t, then the input x of t will produce the same output y of t. So the system that we have on top here and the system that we have at the bottom here, they are both identical systems. So now the system at the top has two parallel systems, each having an impulse response h1 of t and h2 of t respectively, and that produces a certain output y of t when the input is a certain x of t. Now if we replace this combination of parallel systems with a single system whose impulse response is the sum of these two impulse responses, okay? So if we call this overall thing as a single h of t, then the same input x of t would produce the same output y of t as the system on top, okay? So using the distributive property, we are able to represent a set of a parallel system, okay, a system which is a parallel, which has parallel subsystems rather, as a single system whose impulse response is the sum of the impulse responses of these subsystems, okay? Or conversely, if we have a single system whose impulse response is given by a certain value, then we can break this down into multiple parallel simpler systems whose impulse responses are such that the sum of the impulse responses is equal to this overall impulse response. Okay, so we are basically using the distributive property to break down a single system into multiple parallel systems, or to combine parallel systems into a single system. Okay, so that's called as the distributive property of the LTI systems, and we are able to in fact that's a feature of the convolution operation itself. So the convolution operation exhibits this distributive property, and therefore it allows us to represent parallel systems as a single system whose impulse response is the sum of the individual impulse responses. And in that way, the same thing applies even if the system is a discrete time system, in which case, instead of h1 of t and h2 of t, we will have it as h1 of n and h2 of n in square brackets. Okay, so the distributive property applies to both the continuous time case as well as the discrete time case, which we have depicted over here. Okay, so we will now see the third property of LTI systems, which is called as the associative property. Now, the associative property is given as, suppose we have x of t convolved with h1 of t, which is convolved with h2 of t, and let's say we put this in bracket here. So that means we are first convolving h1 and h2, and then convolving x of t with that result, and that is the same as x of t convolved with h1 of t first, and then that result being convolved with h2 of t. So when we have these multiple convolutions, the order in which the convolution is performed does not affect the result. So we can perform this first and then the second one, or we can perform the last two versions first and then convolve it with the first one. So the result will not change in that case. So similar thing applies for the discrete case as well. So x of n convolved with h1 of n convolved with h2 of n. Okay, I'll use round brackets for these brackets because the square brackets represent these argument for discrete case, right? So x of n convolved with h1 of n convolved with h2 of n is the same as x of n convolved with h1 of n first, and then that result convolved with h2 of n. Okay, so the order of this convolution does not affect the result. We can verify that. Okay, you will see that in your tutorial classes as well. When you have these multiple convolution operations, it doesn't matter in which order you're performing these convolutions, the result is always going to be the same. So in such a case, there is no need for putting these brackets here. Okay, these brackets, which is combining two terms at a time, right? Those are not necessary. Even if you mention this without those brackets, there is no ambiguity in what we are trying to represent. So that means we can simply write x of t convolved with h1 of t convolved with h2 of t without any ambiguity, because whether we perform this convolution first or this convolution first, it doesn't matter. In fact, you can perform x of t with h2 of t first and then convolve with h1 of t. The result is going to be the same. So there is no ambiguity in leaving out the brackets, the bigger brackets here. Okay, so similarly, x of n convolved with h1 of n convolved with h2 of n. Okay, writing it this way gives us no ambiguity in what we are trying to represent, because all possible ways of convolving them will give us the same results. So there is no ambiguity in these, even if we ignore these bigger brackets here. Okay, these brackets, if we without that also, it means the same thing, and the result will not be affected. So therefore, that is basically the associative property of the convolution operation, and hence the associative property of LTI system. And this associative property has an implication or meaning when we have systems in parallel. So not systems in parallel, systems in series, that is. So when we have systems in series, what this basically means is that suppose we have system 1 which has an impulse response h1 of t, and system 2 which has an impulse response h2 of t. The order of these systems in a series representation is not important. We can interchange the order of the systems, the two subsystems, and have the same overall response of the system. So that's where the associative property becomes useful. So if we have two systems which are in series with each other, then we can interchange the order of the two systems. And secondly, we can combine these two systems using a single system where the impulse response of the single system is basically the convolution of the two individual impulse responses. Okay, so we will illustrate that with a diagram here. So what that means is, if we have two systems in series, where the first system has an impulse response, let's call it h1 of t, and the second system has an impulse response h2 of t. Okay, so since we can convolve h1 and h2 of t and then convolve it with x of t, so we can combine these two as a single system whose impulse response is a convolution of h1 and h2 of t. So this, when having an input x of t, produces an overall output y of t. So we can convolve h1 and h2 of t, convolve these two, and then convolve with x of t to get the same y of t. So these two systems in series can be replaced with a single system whose impulse response we can call it as simply h of t equals h1 of t convolved with h2 of t. I need to make some space there. Let me write that clearly. So h of t equals h1 of t convolved with h2 of t. So when this system is given an input x of t, it will produce the same output y of t as the series systems here. Okay, so rather than having two systems in series, h1 and h2, producing an output y of t for an input x of t, we can replace those two systems with a single system whose impulse response is the convolution of these two individual impulse responses, and we can have the system characteristics to be the same as these two systems in series. So we are using this associative property to illustrate this. Okay, the same thing applies for discrete time case as well, in which case we will have h1 of n and h2 of n. So whether we perform this first, okay, and then convolve with the input, or we perform a convolution with the first system and then convolve it with the second system, it means the same. And since the convolution operation is commutative, the first property that we saw, h1 convolved with h2 is the same as h2 convolved with h1. So that means we can replace this with the commutative property as h2 convolved with h1, and then split it back with h2 in series with h1. Okay, so that way, basically what we're saying is, when systems are in series, by using the associative property, if the systems are LTI systems, then the order of these systems can be interchanged without affecting the input-output relationship. So basically, we can have a system whose impulse response is the convolution of these two individual impulse responses, which we have depicted here. So h of t is a single system whose impulse response h of t is a convolution of this subsystem's impulse response h1 of t with the second subsystem which is in series with it h2 of t. So we have this single system now. Now, using the commutator property, we can interchange h1 and h2, so we get the same results. The same x of t will give us the same y of t for this one as well. So interchanging h2 of t and h1 of t in the convolution operation does not alter the result by the commutator property. And from here we can split it further to say that we can break it this single system into two systems in series as h2 of t, and in series with that we will have h1 of t, and an input x of t would produce the same output y of t. So basically, if we compare this last figure, which is two subsystems in series, where we have h2 first followed by h1, that is the same that is having the same input output relationship as having h1 first and followed by h2 of t. Okay, so interchanging the systems in series does not affect the input output relationship by the associative property of LTI systems. So again, that applies to LTI systems. So interchanging the order of the subsystems in an if they are LTI, that is linear time invariant systems, does not affect the overall input output relationship. Okay, and that proceeds from the associative property of LTI systems. However, this interchange is not valid if the systems are nonlinear systems. Okay, so we'll give an example for that. Okay, so this interchange is possible only when the systems are LTI systems. So let's look at an example where such an interchange, changing the order of the systems is not applicable, is not valid. If it's an LTI system, it is valid, but if there is nonlinearity in the response of at least even one of the systems, then we cannot interchange or change the order of these subsystems. Okay, so suppose we have a system where it takes an input signal x of n, okay, and the first subsystem has an impulse response which simply doubles what is x of n. So it is just going to multiply it with 2, so it makes it into 2. So the output that we get from the system is 2 times x of n, and the second subsystem is going to square the value. Okay, that means it is going to whatever is the input, okay, it is going to square it. So when it squares 2 times x of n, 2 square will become 4, and x of n square will become x square of n. Okay, so that's the output, overall output of the system. So this y of n here, that's equal to our y of n, that's equal to 4 times x square of n. Now if we interchange or change the order of these two operations, so where we do the square first and then the doubling, let's see what happens. So the first subsystem here is going to perform the squaring operation, so that's the square operation, and this will perform the doubling operation. So the input to the first system is x of n, and the output is going to be the square of that, because x of n squared. Okay, that's x square of n, and that will get doubled. So for the second system, the input is x square of n, that gets doubled, so the output will be 2 times x square of n, which is not the same as the y of n that we have above. Okay, so just to distinguish between the two, what I'm going to do now is I'll call the first one as y1 of n, so that's not the same as the y1 of n. Okay, so this is the output of the second system, which we can call as y2 of n equal to 2 times x square of n, and that is not equal to y1 of n. What is happening here is that the two subsystems have the same are doing the same operation on the input, but now we have simply changed the order of those two systems. Changing the order now in this case is not giving us the same result. Okay, so therefore this changing the order of the subsystems when they are in series is not applicable if there is nonlinearity, because here that's a nonlinear operation. Squaring is a nonlinear operation here. So changing the order of these two systems produces two different results because there is nonlinearity inverse. So this property that we can interchange the subsystems or change the order of the subsystems is applicable only when the systems that are in series are all linear systems. If there is even a single system that is nonlinear, then we cannot interchange the order of the systems, because that would give a completely different response or the completely different output for a given input signal. The next feature or characteristic that we want to, or property that we want to discuss, is about identifying whether the LTI system is a system with memory or without memory just by looking at its impulse response. So by observing the impulse response of a system, of an LTI system, can we say that the system is having memory or without memory? And if you recall, from our discussion a couple of lectures back, where we talked about the properties of systems, in which we discussed about systems with memory and memoryless system. A system is said to be memoryless if the output at any time depends only on the current input and not on the previous inputs. Okay, so that's the system which has a memoryless system. If the output of a system depends on the current input as well as the previous inputs, then we say that the system is having memory. So how do we know? By looking at the impulse response, or what condition should the impulse response satisfy in order for the system to be a memoryless system. So let's look at that. So that's our next property that we are going to look into. So that's called as LTI systems with and without memory. And to understand this, we just need to recall what do we mean by the impulse response. So the impulse response of a system is basically the output of the system when the input is a delta function. That means the delta function is having a non-zero value only when t equal to 0 or n equal to 0. So let's depict that. So to understand that, just recall what do we mean by the impulse response. The impulse response of a system h of n, I've taken the example for a discrete case now, is basically the output of the system when the input is a unit impulse. So the unit impulse is defined only for n equal to 0, and it has a value of 1 when n equal to 0. And that means if we give an input which is an impulse like this, the output is, whatever output we get is h of n. Now we want this output to be independent of previous inputs. That means the previous versions of this impulse. That means h of n should be 0 for all previous values of n, and since we also want this to be a causal system, it should also be you can't have an output before the input, right? So we can't have an output for future impulses. That's not possible. So basically, for this to be a memoryless system, what it means is that this h of n should be non-zero only when n equal to 0. For n not equal to 0, the response should be 0. That would indicate that the system is a memoryless system or a system without memory. So an LTI system is memoryless if h of n is equal to 0 for n not equal to 0. Then we can say that the system is a memoryless system. Then the LTI system is memoryless. So what that implies is that that means the impulse response h of n is basically another impulse delta of n, which is scaled by some constant. So basically what it means is the impulse response h of n is equal to some scaling factor k times the delta function delta of n. So the output of the system when the input is impulse is just a scaled version of the impulse impulse. So instead of having an amplitude of 1 for the impulse, it will be another impulse, but the height will be scaled by some factor k, and that k denotes the value of h of n when n equal to 0. So where k is equal to h of 0. So the value of h of n when n is equal to 0, whatever is that value, that will be the scaling factor k that gets multiplied with this delta of n. So the LTI system is a memoryless system if we see that the impulse response is also an impulse, but scaled by a certain factor. If that scaling factor k is equal to 1, that means the output is equal to the input. So when h of n is equal to delta of n, then we say that we call it as an identity system. That means the system is not doing anything. Whatever input is applied, it is producing the same as the output. So that's when k is equal to 1, or when h of 0 is equal to 1. So when this factor k, let me write that k properly, k equals 1, that is h of 0 equals 1. What is the relationship between the input and output for the when the input is impulse? So the response h of n is equal to delta of n. So when the input is delta of n, we get an output equal to delta of n. So that's called as an identity system, and that occurs when k is equal to 1. So when k equal to 1, the output is equal to the input, and in that case we call it as an identity system. So that means the scaling factor is 1. So the impulse response of the system is also an impulse having a height of 1, having an amplitude of 1. So the unit impulse input produces an output which is equal to the unit impulse. So the impulse response is equal to the input impulse function. So that's called as an identity system. That means the output is identical to the input of the system, and that happens when k is equal to 1. Now from this we can deduce a very interesting property of convolution, and so basically what we see is that from our knowledge about LTI systems, if we know the impulse response of a system h of n, we can find the output to any input signal x of n. So the output of the system to any input signal x of n is basically the convolution of the input with h of n. So that's our input-output relationship for an LTI system. But when the system is memoryless, without memory, and the scaling factor is 1, that is an identity system, okay, for an identity system, okay, an identity system by its definition is a memoryless system, okay, because the input is exactly the output is exactly equal to the input, so it does not depend on previous inputs as well. So therefore the identity system is a memoryless system, okay, by its very definition. So for an identity system, we have the impulse response h of n as equal to the input signal delta of n, which is what we have depicted over here. Okay, that's for an identity system. So for an identity system, this h of n is equal to delta of n. So we can replace this output, and that is going to be exactly equal to the input, right? Because that's an identity system. So y of n is going to be equal to x of n. So that's by definition of the identity system. So therefore, we can write this input-output relationship as y of n as equal to x of n convolved with delta of n, because h of n is equal to delta of n. And because this is an identity system, the output is equal to the input. So the output y of n here is equal to the input x of n. And so x of n convolved with this delta of n should give us back x of n. Okay, because we are dealing with an identity system. So that leads us to an important observation. The observation is that for the convolution operation, the unit impulse function is the identity function. So that means, just like in multiplication, you have 1 as the identity value, right? So anything multiplied by 1 gives the same value. 5 into 1 is 5. X into 1 is x. Similarly, for the convolution operation, any signal convolved with the unit impulse function gives back the same signal. So x of n convolved with delta of n is x of n. U of n convolved with delta of n will be u of n. Y of n convolved with delta of n will be y of n, right? So the unit impulse function is the identity function for the convolution operation, and that is deduced by using these property, by analyzing this property of memoryless system and taking the scaling factor to be 1. So that gives us an identity system. And from the definition of the identity system, we can now deduce that the output has to be equal to the input. And because the impulse response is equal to the input impulse function, we replaced h of n with delta of n. So now x of n convolved with delta of n should give us x of n. And therefore, that means this delta of n is the identity function for the convolution operation. So we can extend these ideas to the continuous time case as well. So in the continuous time case, so similarly in the continuous time case, the system is memoryless if the impulse response h of t equal to 0 for t not equal to 0, or in other words, what that means is, it means that h of t equals a scaled version of the input impulse. Okay, that is k times delta of t, where k is equal to the value of the impulse response at t equal to 0. K is equal to h of 0. And since this is continuous time, the brackets is rounded brackets. Okay, that's h of 0. So when k is equal to 1, again we get the identity function. When k equal to h of 0 equals 1, the system is an identity system. Identity system. That means the impulse response h of t is equal to the input impulse unit impulse delta of t. So based on that, we can similarly write y of t is convolution of x of t with the impulse response h of t, which is equal to convolution which should be x of t itself, because this is an identity system now. Okay, because we have made k equal to 1 in this case. It's an identity system which is a memoryless system, so that's equal to the output is equal to the input. Now h of t is equal to delta of t, so x of t convolved with delta of t, that's equal to x of t. So we again have here that anything convolved with the unit impulse function gives us the same function. So x of t convolved with delta of t gives us x of t. It's like 5 into 1 equals 5, or m into 1 is m, right? So just like 1 is the identity value in the multiplication operation, the unit impulse function is the identity for the convolution operation. So anything convolved with the unit impulse function gives us the same function, whatever that is being convolved there. Okay, so that's another interesting observation about the convolution operation itself, where we see that the unit impulse function, whether it's in the discrete time domain or in the continuous time domain, the unit impulse function is the identity for the convolution operation. So we have seen here this property, which is which allows us to identify whether the LTI system is a memoryless system or with memory. If it is memoryless, h of n should be 0 for n not equal to 0, or h of t should be 0 for t not equal to 0 if it's a continuous time system. Only then it's a memoryless system. If h of n or h of t is having a non-zero value for n not equal to 0, then automatically we can say that that system is a system with memory. It is still an LTI, it could still be a linear time invariant system, but with memory. Okay, so we can identify whether the system has memory or is it without memory, depending on by observing its impulse response. Okay, there is one or two more properties that we want to talk about, and that's called as the invertibility property and the causality property. Again, we'll wind up for today. We are out of time, so we'll stop here for today, and we'll continue with the last two properties, which is the invertibility and the causality properties. Again, these are properties which we have discussed before when we talked about system properties, but we are going to analyze it in more detail and try to identify whether the system is invertible or not, whether the system is causal or not, by observing or looking at its impulse response. Okay, so how can we determine whether the system is causal or not causal, whether the system is invertible or not invertible, or whether the system is having memory or not memory, by observing its impulse response. Okay, so we will continue with those last two properties in the next lecture. We'll stop for here for today.